and welcome. Today we're doing a question from LeetCode called Implement Trie. It's medium and a question I really like, so we're going to go through it together. It's going to be a lot of fun. Let's get into it. A trie or prefix tree is a tree data structure used to efficiently store and retrieve keys in a dataset of strings. There are various applications of this data structure, such as autocomplete and spell checker. So let's see what this link is, and you can view this article on your own time, but it gives basically an overview of all operations you can perform on it, and we even have a little diagram here. Basically, we have a root, and this is what our tree structure should sort of look like. We have letters, so T, E, A, to form the word T. Okay, so back to the question. We want to implement the class. So first thing we're going to do is initialize the object. The next thing is inserting a word. So the function insert inserts the string word into the trie. Now we have a search function that searches for input word and returns true if the word is already in the trie or if it was inserted before. And of course, if it can't find it, we return false. Another function is StartsWith, and we're given a prefix. This returns true if there is a previously inserted string word that has the prefix. And of course, if we can't find it, we return false. So this is sort of a modification on the search. Essentially, we want to search not for a word, but if certain letters already exist. So to recap, the four things we want to do here: initialize, insert a word, search for it, and search for a prefix, which is kind of a modification on search. Example 1, we have the following input, and let's see how this is working. We first have the trie that we are creating, and now we want to insert the word apple. After that, we search for it, and since we have already inserted it, we return true. Next, we search for app. So we return false here because we've never inserted this word. For when we do a starts with app, that prefix does exist. When we had inserted apple, we came across app, so we return true. And when we insert app finally, and then make a search for it, at this point, instead of returning false, we return true. We have some constraints here, but essentially this is the structure we want to implement. Now, for this problem, there are a few things we do need to do, which might seem a bit involved. So let's take a look at the first example again and really make sure we know what's happening. So in this first example, this is our input, and we can actually just read it like this to make it more easy. Okay, so we have this structure that we are inserting and searching for words, right? And it said in the beginning that this is a type of tree data structure. So how do we actually want to build this? What we can do, instead of, say, a binary tree that has left and right nodes, left and right children, we can just open it up to have a dictionary so we can have as many children as we want to take care of any character that we come across. So any node will have up to 26 children, A to Z. So with this example, right, let's say I start off with my root node. The first insert I do is apple. So going character by character, I insert apple first. So the first thing I'm going to insert is A. And now it's P, another P, because I'm just going to go down my word. So every single character that I come across, A, P, P, L, and finally E. Okay, so I have A, P, P, L, and E. The next thing I do is I search for this apple. So I'm going to go back into my structure and see if I can find all the corresponding characters. So I see an A. Now I want to see if A's children has my next character. So does A's children have P? It does. Now at this node, I want to see, does another P exist in this node's children? It does. And same, L and E. So since we've seen all these characters, we would return true. Now we want to make a search with APP. So we see A, we see P, and we see another P. But we actually have to return false here because it wasn't a word we inserted. It's just part of another word that we have inserted. So how do we actually differentiate when to return true or false for a word that we're searching? What we can do is just add another Boolean flag. So at my nodes, at every node, I have a set of children. I can also add another field called word, for example, to indicate whether or not I'm a word. So at APPLE, once we've gotten to E, I'm going to add another field, say it's word, set to true. So if this is true, then I know that I have formed a word. So if that true flag is not there at P, I know to return false. So here, this is not a word yet, and I will return false. Now when I search for a StartsWith app, APP, just existing is enough. We don't actually need the word to be there. Now I'm going to go ahead and insert app. So APP, it's already there. The only thing I need to do now is set this to be a word. So now when I do search for it, APP at P, I see that this is a word and I return true. So that is all we need to do. This is how the structure will look like. The only thing left is to code it up. So we're going to go ahead and code this up together and then do a walkthrough to see exactly how this is being built. Okay, so what is the first thing that I want to do? I want to initialize this try object. And remember, we want two things here. One, we want to know what children we have, and two, whether or not this node actually marks the end of a word. So for the first one, I'm going to have self.children equal a dictionary. And in this dictionary, the keys are going to be letters. So every character that we come across in our word. And the values are going to be try objects themselves. And for my second field, let's call this word. And this is actually going to be initialized to false because unless we explicitly set it to true, any new try object that we create can't mark the end of a word. So this is what I'm going to do to initialize my object. Now, if I want to insert a word, what do I do here? The first thing I'm going to do is actually go ahead and rename self to be root just because it's more clear. So now we have our root. I want to insert my word into this structure. Well, first of all, let's loop through every single character that we want to insert. So for character in word, we want to see if this character already exists in our node's children. If it doesn't, then we want to go ahead and create that child. So add it to this dictionary, and for its value, initialize a new object. So if character not in root.children, well, now I want to add it in. So root.children of that character. So at this key, I'm creating a new try object. So at this object, I have no children and word is marked false. And this points to the character that I've just created. So if this was apple, right? A-P-P-L-E, if we were inserting it, I would start off with root being nothing. So this is just root. And the first character I come across in my word apple is A. I see it doesn't actually exist there. And again, this is if this is my first time doing it. So I just have root, I have nothing else. I just have that this is not a word. So word is false. And it has a dictionary of children that has no keys. So I see that A is not in my children. I'm going to go ahead and add it in. And A is now going to have its own set of children because I'm initializing a new try object. So A has its own set of children and its word is set to false as well. Now here, what am I going to do outside of this if condition? I'm going to set my root to be root.children of that character. So before I had root pointing here. I am now going to point it here because this way I can build off my entire word. I want to add PPLE and I want to go down. So if this is my new root, I am back into this for loop. My next character is P. I see that P is not in A's children, in my root's children. So I'm going to go ahead and add it in. So root.children at P is going to equal a new try object. So this will have a set of children at P, and this word is going to be false. And once again, I set my root to be that of P's. And I do this going down. So A, P, P, L, E, right? So A, P, P. Of course, this also has empty children. And last one is E. So once I am at L, right, I see that E is not in my children. I go ahead and add it in and initialize a new object. Now I go ahead and change my root. So now it points to E. What's the last step I want to do to mark that this is a word? I need to set my root.word, because this now points at my last node, to be true. And that's all we need to do for insert. So this is now going to be true, and we've just inserted apple into our structure. Now I want to search. Okay, so 2 down, 2 more to go. We want to search for this word. Again, let's rename self to be root. I'm going to iterate through word, so for character in word. What checks do I want to make? I want to see if this character exists in the children of my root. If it does not, well, now I can just return false right away. So if character not in root dot children, return false. If it is there, we just want to go down. So I'm going to set root to be my root dot children of that character that does exist. In the very end, what do I want to return? So doing this will get us to the bottom of wherever we want to go. So say we're searching for apple now, right? It's essentially very similar to the code we've just written. So we're just going to be going down, right? We're setting root to be that character each time. So it keeps going down. And at the very end, we just want to see what the value of word is. So we're going to return root.word, whether or not it is true or false. So say we inserted apple and we searched for it, we would return true. Now we search for app. So A, P, P, it's false, so we return false. And say instead of apple, we are searching for banana. B doesn't even exist, so we would return false right away since that character is not in any of the children. Now, we want to do starts with. This is very similar to search, so I'm going to go ahead and copy paste this whole thing in. The only difference here is that we don't want to return whether or not we're at a word. We just want to know if those characters exist. So if we've made it all the way down, we've gone through our entire for loop and we've gone all the way down, we've seen all the characters we want to in our prefix, and we just return true. We don't care whether or not that node marks the end of a word. So root equals self for character in prefix. If that character is not in my children, I would return false. Otherwise, I would set my root to be that child, and I keep iterating down. If I've made it all the way to the end, I return true. And that is it. We've implemented the structure. Let's go ahead and run this code. It's accepted and submit. And accepted as well. So before leaving, let's go through an example. And what I'm going to do is insert app, then bat, search for A, starts with A, insert bat, and search for it. So we initialize it, we insert app. When we search for bat, this should return false. If we search for A, this should return false. If we do starts with a, that should return true because so far we've inserted only app. And then we insert bat, so we have app and bat. And if we search for it, this should return true. So let's take a look at our functions. I go ahead and initialize my new try. So this is root. It is not a word, because remember I said it's no word, and it has some children. These are its children. First thing I do is I insert app. So in my insert function, root is self, so this is root right now. Root here. And I'm iterating through my word. First thing I'm on is a. I see that a is not in my children, so I add it in and create a new try node. So I add it in, this is a, word is false, and I add children for it. Now I make root this new character that I just added as a child. So root is now this. And I'm back in my for loop at character P. So I do the same thing again. P is not in my children. I can go ahead and add it in. So P is not a word, and it has its own children. And we set root to be this right here, and we do the same thing again. So this is P, and at this point, I actually, at the very end, where is this insert? At the very end, I set root to be true. I can go ahead and set my word to be true. So now I search for bat. I have my root here. I look for B in its children. It does not exist. I return false. I search for A. I am in root. A does exist. And while I'm searching for it, so for character in word, I start with A. If it's not in my children, I would return false, but it is. So now I have root here, and I return whether or not it is a word. It's false, it's not a word, so I return false. Now I do a starts with for A. So A is my prefix. I am at root for character in prefix, so for A so far, is that character in children? If it is not, I return false. It is in my children, and I set my root to be that character, so this is now root, and I would return true no matter or not this is a word. This exists, it's a prefix, we return true. Now I insert bat. So B-A-T, I go ahead in here and I insert it. So for character in word, I am at B. If it's not in my children, I go ahead and add it in. So B, word is false. And let's add a line here to mark that this is also coming from root. Now this has children of its own, so here we initialize to be empty. So now we go ahead and add a, word is false, it has its own children, and I finally go ahead add in t, which is false, but at the very end we do mark it as true. T-R-U-E, okay, and T also has its own set of children, and P should have also had these, so let's add that in here. They're just empty though. Okay, so now we've gone ahead and inserted bat. So now when we search for it, so root at self, for character in word, we search for B. Does B exist in my children? It does now, so now I set root to be here. So this is my root here, and I go back into my for loop. Now I search for A. Does A exist in my root's children? It does, so now root is here. Now I do the same thing again. I go down. Does T exist in my root's children? It does, and I just return whether or not this is a word, which is true. So hopefully this example gave you a clear understanding of what this structure looks like. Essentially, instead of left, right, nodes and values like we would do in a binary tree. We have a dictionary to save all of our children, and a flag to mark whether or not we're a word. If you have any questions at all, let me know down below. Otherwise, I will see you next time.